So we're going to do an average calculation, an average or expected value calculation on our calculator. And the way we're going to do that, we're going to use our snow day data to do this. When I get into my calculator, I'm going to go to stat number 1 edit, which is our old favorite, stat edit. Now, if my 6th period students did this, you might see the data from the snow day data in the calculator. If not, you might have to, or if there's other data there, you may have to just type over it. But here's what I'm going to want to do. I'm going to put all my X values in list 1, and I'm going to put all my P of X values in list 2. So my X values are 0 through 10. So if I type and press enter, you guys can do that faster than I can put the information, all the possible values for X, 0 up to 10, in L1. Okay. So those are all my X's. And then next to each X, I'm going to put the probability that goes with that X. So 0.33 next to 0, because it's a 33% chance I'm getting 0 snow days. And 0.19 next to 1. 0.14 next to 2. And so on. Just taking these right from my table. Putting each individual X and its related P of X. And I'm being really careful that I'm putting the decimal points in. So 0.1 for the 10, 0.10, 0.07, 0.05, and then I've got 0.04 for 6, 0.04 for 7, 0.02 for 8, 0.01 for 9, and 0.01 for 10. Okay. So every X that you have has a probability that goes with it. We're talking about a discrete random variable, so individual counting numbers, individual probabilities. Once we get all of that information in there, then the next thing we do is we go to stat, we go over to calculate, I'll move that out of the way, and we go back to our one variable statistics that we used in the past. Like, okay, that's cool. So stat, over to calculate, number 1 for one variable statistics. Here's where the change happens. And I already have it like this on my calculator, so I'm not going to have to redo it, but I'll tell you what, I'll delete it and redo it. So when I go to this screen, it used to be when we were using this one variable statistic function before, all we had to worry about was one list of data. Now we have a list of variables and a list of probabilities. So the list, where it says list, that's where I want to put wherever my X's are. And it's easiest if you put those into L1. So list needs to have L1 next to it. And frequency list needs to have L2 next to it. Now the way you can get L2, just to remind you, the numbers 1, 2, 3, 4, 5, 6 have L1, L2, L3, L4, L5, L6 in a different color that matches up with your second button. I don't know what it is on the yellow. Oh, it is blue on yours. Okay, so if we hit the blue second button and hit a 2, second 2 gives me L2. And then, so if I have the L1 and the L2 and I calculate, it's not averaging L1. It's taking L1 times L2, multiplying them together, and totaling them up. L1 times L2 the average for that is 2.17. So that means we're going to expect an average of 2.17 snow days. Some years will have more than that. Some years will have less. More years will probably have less than more. But if we went over 20 years and I counted up how many snow days were in every year and averaged them together, if we're still following kind of this probability chart, we're going to expect about that many snow days, about 2.17. It makes sense because if you look at the data, 33% and 19%, that's already like 52% of the snow days are 0 and 1. The other half of the snow days are 2 through 10. So every once in a while we might have a bigger one that brings the average up a little bit. But 33%, 19%, most of them are down here. We're going to expect about 2.17. Now the weird thing is, it's okay that this expected value is a decimal, even for when you're working with a discrete random variable. That's going to happen. So it's okay to get a decimal on this, even if you start with something that's discrete. Now, if we use our calculator to do the expected value, the standard deviation is also right there on the screen, about 2.41 is my standard deviation. So that means if I was going to talk about, well, you know, what's the variability in number of snow days? There's about an average of 2 per year. About how does that fluctuate? It fluctuates like plus or minus 2, plus or minus 2.5. So we have usually have about 2 snow days on average, plus or minus 2. So anywhere from roughly 0 to 4 is an expected, is a kind of another way. So the mean, the average expected value tells you a single number to expect. When we put the mean and the standard deviation together, that gives you kind of a range of snow days to expect. So if we take our snow days and we take our x bar plus our sigma and x bar minus, that's our lowercase sigma, it kind of gives a range of things to expect. Okay, so our 2.17 plus 2.41, 2.17 minus 2.41. Well, in that case, this is negative, but we can't go lower than 0. So we're going to just say our bottom restriction is 0. Our upper restriction is like about 4.56. So we could say, all right, I'm going to, if I had to make another statement, I could say, well, I expect 0 to about 4.5. So maybe I round that to 5 snow days. If you were going to bet, you'd say, oh, I'm going to bet on about, you know, if I was going to pick a number to bet on number of snow days, 0 to 4 is probably a pretty safe bet. 2 is a really good bet because that's usually the average. Okay. 1 year might be 8 and 1 year might be 0. But over the long run, we're expecting about 2 per year. So that's how we're going to use our calculator to put the data in. You can always and do the expected value and the standard deviation. Now, standard deviation, there's a way to do that without the calculator. It's a little bit more complicated formula. So that is definitely something you're going to want to get from the calculator. The expected value, it's not so hard sometimes to multiply x times p if the chart isn't really long. So let's look at this telephone problem and use this to wrap up. Okay. So this is data from 1994 where people were reporting in their data how many landline phones, how many actual physical phones they had in their house. Okay. Growing up, we had 3 for a long time. We had one that hung on the wall in the kitchen. We had one that hung on the wall in the basement. It was like a finished basement. And then there was one in my parents' bedroom, plugged in, like sitting on their table. And then when I got older, I had a phone jack in my room, so I think I got a phone, and so I had a phone in my room. My grandma's house had 2. She had one on the first level and one on the second level. Some people just had one. Like that was, it's kind of, as time went on, more people had more homes. But so what we saw in 1994 is 3 or more was very common. 2 was very common. Not having any phone, any landline, was very uncommon. It'd be interesting to see what this is now. And so we can determine the missing value if I have the 0, 1%, and 31%, and 57%, which is 0.89. That would mean we would need about 11% having one phone. So this is definitely discrete. We're counting phones, so we're not going to have decimals. We have 0 or 1 or 2 or 3 or more. The probability that x equals 1 is 0.11 or 11%. The probability that x is greater than 1, well, x is greater than 1 in this problem means x equals 2, x equals 3 or more. That's 0.31% for 2, 0.57 for 3 or more. And so, it's about an 88% chance that if you randomly picked a house in 1994, that they would have more than one phone in their house. And then expected value, what would be the average number of phones we would expect? Well, 0 times 0.01, if we were going to do this by hand. 1 times 0.11. 2 times 0.31, and then when it's 3 or more, we usually decide, okay, we're just going to use the low end. So I just use 3 for that. So I can do it that way and do that calculation. Or, so quickly I can do this. I can do, if I want the calculator to do it for me, the 0.01, and then the 0.11, and the 0.31, and the 0.57. Right. We'll delete all the rest of the data. So I have my L1 and my L2 organized. I go back to stat, over to calculate, one variable statistic. I need to just make sure these are both there. If you just have L1, it's just going to do L1 work. If you have L1 with a frequency L2, then it'll do this kind of average that we're doing. And we would see we're going to expect an average of about 2.44 phones per home with a standard deviation to give us kind of a range of about 0.73. Okay. So when we come to class on Friday, first of all, let me stop this. I will post this video along with a copy of the notes so that any